In the monsters, the powerful impact of supermassive black holes on their...
Non vi sento più, però. Non vi sento più, però. Sì, perché non vi sentivo più, non capivo cosa sta succedendo.
Ok, sorry.
Sì, perché non vi sentivo.
Okay, Deborah, sorry, you didn't hear me. So, it's Alessandro Marconi, I'm chairing the session. Good morning, Deborah.
Hello, hi.
I think that Beta will somehow let you know when you have 5 minutes left, okay?
Okay, sounds good.
Okay.
The stage is...
Whenever you want to start, the stage is yours.
Okay, perfect. So thank you very much for this lovely invitation to attend the conference. And my apology for not being able to be there with you today. So I will very much miss all the science and all the fun in Firenze. So today I would like to tell you a little bit about feeding the monsters, the powerful impact of supermassive black holes on their environments. And I would like to acknowledge my team of postdoctoral researchers and PhD students listed here. They have been working hard on these topics for now a number of years. So I would like to start with a little bit of introduction and observational evidence. I'm sure you have heard a lot about this during this conference, but we have really, from the observational standpoint, at least in the case of radio jets, but more and more so in case of also AGN accretion disk-driven outflows, evidence that the feedback from supermassive black holes must be important in shaping the properties of galaxies and galaxy clusters, and that these sources are energetically really, really powerful. The field is actually moving quite rapidly. It is absolutely amazing, the most recent developments in observations of supermassive black holes. I like to show this image of the M87 and the emergence of jets from it. And now, essentially, we have a picture of this process close to the event horizon of the black hole, thanks to the EHT telescope, and all the way out to the large scales where these jets interact with the intercluster medium. And not only that, we have this range of spatial scales that we are starting to resolve observationally, we have a completely multi-wavelength picture, which is really amazing that we can study this object now in this great detail. And another paradigm shift observationally that is happening is detection of more and more sources with seizable AGN outflows or jets in objects that would be traditionally perhaps less expected, such as the AGN jets in XIV galaxies. And here I'm reporting a nice paper by Venturi and collaborators. And also in the jets where traditionally the sources have been labeled as radio quiet quasars. And also very intriguingly, there is this emerging field of active galactic nuclei even in dwarf galaxies, with at the moment puzzling evidence whether these black holes could actually influence their hosts or not. So this is a very active field of research. So I'm coming now to the theory, and I would say that this is a bit of a kind of an iconic image that has guided theoretical and numerical simulation work already for a number of years. So this plot is showing the stellar mass of a galaxy over its halo mass, normalized by the universal baryon fraction in the universe as a function of the halo mass itself. And the majority of curves that you have to see here, you no need to go into the details of the curves, are based on these abundance matching techniques, where every dark matter halo is assigned a typical stellar mass. And on top of these bands, essentially, there are a number of simulation results as well that are trying to reproduce this abundance matching techniques that essentially have been calibrated extensively on observational data. And from this, there was a bit of a standard law emerging that for the low mass galaxies, one needs to invoke a very powerful stellar feedback to regulate their star formation rates and hence the final stellar masses, while at the massive end, it's really the AGN feedback that has to be included in cosmological simulations of structure formation to be able to reproduce realistic galaxies. I have put, as you can see in the title, a little bit of a question mark here. I think this is really a kind of a first guidance, a very rough picture. And with the emergence of the AGN in all these now smaller mass galaxies and Seyferts and dwarfs, it will be really interesting to revisit this. But it's a little bit early to provide a comprehensive view right now. Anyways, bearing this in mind, I would like to emphasize, so this is plot is taken from the Illustris TNG project, that basically all major simulation projects from many different groups that have been performed over the last 5 or plus years, they all, to reproduce realistic galaxies at a massive end, they need to invoke some sort of powerful feedback from supermassive black holes. Otherwise, we have the standard overcooling problem, and we have the problem that we are producing massive, dense disks, which are very star-forming in the local universe, and it's nothing like observations. And the failures of such models are more than an order of magnitude or larger. So that we have a really significant problem of conversions of gas into stars, unless we invoke supermassive black holes. And that has been found by across many different groups, adopting different codes, different methodologies, how to treat various physical processes that regulate star formation in the galaxies. Just to being slightly more specific, these are some salient examples of this need to invoke supermassive black hole feedback from Illustris, Eagle, and Horizon AGN. And I would like to pause for a second on the Horizon AGN simulations, which they have really this lovely visual. They have done the same simulation twice, once with AGN feedback and once without. And every column, the first column is with AGN feedback, and the second column is matching exactly the same object living in the same dark matter halos without AGN feedback. I don't know whether you can see my pointer. And essentially, what you can see here is a nice quenched red and dead galaxy, massive in the local universe, simulated universe. But here you would see this completely overmassive this galaxy with a huge star formation rate, which is clearly ruled out observationally. So this is where theoretically this need for supermassive black hole feedback comes. And obviously one can play with feedback from supernovae and other stellar sources, but as much in the parameter space, which is physically reasonable, one cannot actually get to these results otherwise. So let me now jump a little bit in a kind of a very quick review. If we want to model the supermassive black hole feedback, what are the key ingredients that we actually have to put in these cosmological simulations of structure formation? And here I'm showing a nice cartoon, the visual from Janice Green Nature paper. And essentially there are 3 regimes that we have to care about and try to model. This is at all how the first supermassive black holes emerge, so the seeding process. And then once they are seeded, once they exist in the high redshift universe, the idea is how do we actually model their growth, cosmological growth, which we know that mainly occur through gas accretion, but also we have to, due to the hierarchical structure formation, worry about the mergers of the black holes and how the essentially black hole mass is reassembled due to the mergers of galaxies and therefore their host black holes. And obviously, as I will come later in the talk, that has significant implications for the upcoming LISA space mission. So I wanted to summarize here the caveats and issues in cosmological simulations. I actually have been showing this slide for a few years, and the field is still roughly there, so not major updates and a little bit, of course, but these are still kind of the main caveats that we are faced in these type of simulations. So obviously all these 3 channels, the seeding, the accretion, and feedback, are very complex to model, and there has to people assume some really simplistic models to try to overcome the complexity and to try to at all execute such simulations. So, for example, in the seeding regime, majority of the models assume extremely massive seeds. These are 10 to the 5, for example, in illustrious TNG, 10 to the 6 solar masses. And this really helps kickstart early black hole growth with obvious implications for high redshift quasars. And also to help the growth, majority of models assume a very high occupation fraction of supermassive black holes. Seeds in high redshift universe, and this is also questionable. Then to come to the accretion, obviously to simulate the regions closer and closer to the black hole where angular momentum barrier is so important, is extremely computationally demanding. So majority of models assume really simplistic von Hoyle-like spherical symmetric accretion models, and that helps to kickstart early black hole growth. So this is these models are tuned for some types of growths, and it's very easy above certain mass to reach the Eddington limit. So to say some of the things that may go wrong with this, apart from the usual angular momentum problem, majority of models neglect various other early feedback processes which may remove gas in the vicinity of these nascent supermassive black holes, such as radiation from stars, because while we have RT codes on the fly nowadays, these simulations are quite expensive and quite rare. Majority of simulations neglect the local impact of stellar winds on the environments of growing supermassive black holes. And also, there are very simple models how AGN feedback is modeled, and that usually goes in the category of the buzzword of a thermal dump, even though people are trying to move away a little bit from this. And finally, important thing to say, in majority of these the simulations that I have showed you, the compilation from illustrious TNG of all these different projects, majority of spatial resolution here is still at best of hundreds of parsecs, and rarely with the zoom-in techniques people can push to resolutions better to this. So obviously, we have to be very worried what is the predictive power of these types of simulation given a very limited spatial resolution in vicinity of the black holes, where we are nowhere near starting to resolve the accretion disks around the black holes, and how we can actually ultimately learn about the underlying physics rather than subgrid physics from these types of simulations. So in this talk, I would briefly like to kind of review these various assumptions, try to relax them, and tell you a little bit how the results may change, and what could be the avenues looking forward where we could start to learn more about the physics of these extremely exciting objects. So the first thing I want to briefly mention is the seeding. So this is based on a paper published a few years ago by my former postdoc Colin de Graaf, and we did a very simple exercise. We have compared the standard seeding models that I just described, as for example adopted by the illustrious project, with a very different seeding model that more resembles what one would expect within the direct collapse scenario. So again, one would have massive seeds, but these massive seeds would form in really special halos that have low spin and that are not metal enriched. So you would form much fewer seeds in this particular case. And just focusing essentially on the panel showing the luminosity functions, perhaps on the right. So if one contrasts these purple lines, which would be the seeding model based on direct collapse ideas, versus the black lines, which would be outcome from the illustrious simulation, and then we explored all the models in between, one can see that one can start to learn something about seeding if one starts to probe the faint end of the quasar luminosity function and also especially its redshift evolution. So this brings great hope. Obviously, these models are degenerate with accretion and emerging scenarios, but it brings really a hope that with a next generation observational facilities such as Athena and LIX and so on, that we can start tapping into this regime of faint objects which are really starting to bear memory of the seeding and are more sensitive. Similar things could be said for essentially the scaling relations of the black holes. Once we start probing into the smaller and smaller black hole masses of the scaling relations, which quite a few people observationally are working hard on, and on their redshift evolution, we have ways to start to break these degeneracies in theoretical models and to start to favor more one seeding model and another. Another way how to deal with that, and this is potentially even more powerful way, but we have to wait perhaps a little bit longer, is to rely on LISA data when it becomes available. Again, this is a bit of a busy plot, but if you just look above on the top panel here, this is number of black hole mergers above some redshift in the Illustris type of simulation and in the model where you significantly change the seeding prescription. And the bottom line is, regardless of the primary black hole mass that you put in as a cut that goes into your number of mergers that you are detecting, you can have differences in the results of an order of magnitude or more, which is really significant. So if you transfer that into the chirp mass of the two black hole mergers that LISA will be able to detect, so LISA sensitivity curves are plotted here as a function of redshift, you get actually two quite different histograms that LISA will be able to distinguish. So you can then imagine that LISA combined with electromagnetic observations is going to be very powerful tool to start breaking these degeneracies more and learn about the seeding prescriptions. So moving on, I want to switch topics quite a bit now, and I want to tell you a little bit about supermassive black hole feedback in galaxy clusters, and especially in their heating of the intercluster medium, the well-known overcooling problem, and how to solve it. So this is a really hard problem, and many people have worked over many years to try to understand, and there have been many models proposed how actually AGN jets emanating from supermassive black holes in galaxy clusters may be transferring their energy to the surrounding medium and heating the cluster cores. So obviously there was the idea about the sound waves, then perhaps shocks, but the strong shocks are ruled out observationally. There have been ideas about the gravity waves, about turbulence that has been highly debated, and also just kind of fluid instability type of mixing ideas. So I want to tell you a little bit what was our recent take on that. So this stems from a number of papers that Martin Byrne, a postdoc currently working with me, has been developing and working on. So I wanted to show you here, this is a visual, panel A, of a large-scale environment of a galaxy cluster. This is the virial radius, and this tiny kind of pixel speck in the middle, where is my mouse pointer, essentially that is, we are trying to essentially define new resolution elements in this region. So we are doing something that's called super Lagrangian refinement. We are pushing all resolution in the central region where supermassive black hole resides to be able to follow the jet that is launched by this supermassive black hole. And this is shown in this panel B. So this is, as far to the best of my knowledge, in a cosmological simulation, one of the highest resolution simulations of a jet propagating through this. So you can see this is volume rendered jet morphology and how it looks like. And you can actually zoom even further, so the resolution is high enough to do that. And we are reaching here of tens of parsecs of resolution. So if you, for example, zoom in into this green dashed region, you can see also all these lovely streamlines, velocity streamlines, and you can see the kind of the kinetic dominated jet region, and then you can see the fluid instabilities, and you can also see the contact discontinuity further out at the end of the cocoon. So what can we learn from these very high resolution simulations of jets propagating in realistic galaxy clusters from cosmological simulations? So the first thing, obviously, we can try to see how much they resemble the observations. So here on the left is an observation of the cluster MS0735, and on the right is our simulated cluster. So the pink is showing our mock radio emission that to be compared with observations, and the blue haze is showing the MOX X-rays, where you can find these famous X-ray cavities where the lobes reside. And we are starting to reproduce objects that actually start to resemble observations that we were quite pleased about. But actually, what is important is to quantitatively understand what these jets are doing. So I'm trying now to quickly tell you a little bit about this. Essentially, I want to underline the physical mechanism by which we think the jet lobe energetics is transferred into the intercluster medium. And essentially, it's a two-phase process. So initially, majority of the energy of the jet is in the kinetic form, and this is done by construction. So the jet is kinetically dominated. And you can see that in these curves here. So initially, all of the energy is in this red line here. What quickly happens is that this energy is transferred from the kinetic into the thermal form. So why does that happen? So if we now focus on these colorful panels here, so what we are seeing with these purplish and blue colors is essentially internal Mach numbers within the jet lobes. So as the jet is propagating, it is sending a bunch of internal strong shocks within the jet itself that nicely corresponds to the jet knots. And these internal shocks that can be as high as Mach numbers up to 8 thermalize very efficiently the energy, the initially kinetic energy from the jet. Once that happens, as the jet is propagating, the jet is at the end of its lobes communicating the energy via weak shocks into the surrounding intercluster medium. And it's very important to highlight these are then actually weak shocks, and these are highlighted with these yellowish colors. And these are Mach numbers less than 2 in agreement with observations.
So you have 5 minutes.
Yes. Once the kinetic energy is quickly thermalized, then this is communicated via these weak shocks and PDV heating and mixing. So this is how we think that this process may actually operate. So all kind of standard physics, if you will. And then what Martin has further done, he has explored these jets for a number of different powers and energetics, and he has found that depending of the jet energy that you put in, you can get kind of the full range of observed sources from FR1s to FR2s. But also what he has found, importantly, that the heating of the intercluster medium is a gentle process. And once you have one jet episode, you can working on trying to kind of refine, that is to couple them fully cell-consistently with a gas accretion prescription that essentially, I won't go into details, we have a number of papers, method papers published on this, but essentially what we are doing, we have our resolve simulation here, and then at the boundary where we cannot resolve, we are actually having a subgrid Shakura-Tsunayev disk through which the material is accreted in the steady state, and that ultimately powers the jet where we use the Bluntfeld-Zanaev jet formalism fully, and also we parameterize everything based on the latest GR-MHD simulations. So this work has been largely led by Rosie Talbot, my current PhD student. So what she has been finding with these models, first implemented in a kind of Seifert-like environments, that the properties of the jets and the outflows can change dramatically based on many, many different properties. So if the density of the surrounding CGM medium changes, the jet properties change. If one changes the properties of the disk from which the material is accreted onto a black hole, the properties of the jets and the outflow change. And crucially, if one changes the spin direction or launches the jets within the galactic disk, one can get very, very different outflows. So it's a really complex, messy interactions between these jets and their surroundings. And I won't have much time to cover this, but I just want to highlight we have studied actually quite a bit in detail what is actually driving the accretion once you have the jet that is switched on. And in these particular simulations in the Seyfert galaxy context, we have this intermittent accretion onto the black holes, and we have actually found that the jet itself through the black hole, the backflows and through the vortices that develop in the region surrounding the black hole, and here we are actually barely resolving the alpha disk itself, this material is falling back and reactivating the jet activity itself. So I wanted to now highlight in the last couple of slides, if I have time, just a very recent results. So this is all unpublished, as is all in prep. Simulations are actually still ongoing. Rosie has been now applying these models due to some refinements that we can now run these simulations for a long times to the context of the galaxy mergers, where you would have two supermassive black holes with two jets being active. And these are some kind of lovely visuals of her simulations, where the galaxies come at the first pericentric passage when they start to approach the merger, and during the merger, and you have two essentially distinct jets initially, then you have some intermittent jet activity during the merger, and finally at the coalescence stage, you're driving this powerful jet activity. But what is really exciting for us is the outflow is fully multi-phase, even though the jet becomes strong. So you can suppress at the same time star formation at the black hole coalescence in a merger. But if you look at the properties of outflowing material, you have a range of velocities and you have a range of cooling times in these outflows, so both hot and cold outflows. And of course, with the Muse and ALMA data, this is going to be really exciting to compare to and understand better. So I'm probably running out of time, so you should stop me if I shouldn't speak anymore. But I wanted to highlight the very last result, and this is about gargantuan black holes. So there is this really amazing observations that potentially hint at the existence of 10 to the 10 solar mass black holes at redshift of 6. This is theoretically extremely hard to understand how they come about. And very recently, so these are plots from yesterday, my student Jake Bennett has been doing some simulations and trying to actually reproduce the growth of such monsters, such supermassive black holes, and this is actually possible to achieve within lambda CDM cosmology and actually in different channels, relaxing some criterions about the accretion onto the black hole, so going into the mildly super Eddington accretion of a couple of times, and one can actually reach the luminosities which are agreement with these extreme objects touching upon 10 to the 48 ergs per second. And the impact of these beasts is really amazing. So this is maybe taking it with a grain of salt. These are maximum impact that one can have. One can have spreads of metallicities to 2-3 times virial radii, and one can have clear signature in the thermal AZ effect, which ALMA potentially can detect. So I'm sorry I'm running out of time. I will wrap up now. I just want to say the future of this topic is extremely bright. Obviously, we now have JWST. We are looking forward to the data that's coming this summer. We are going to have Athena, LISA, and SKA. And a little bit more specifically, this is the parameter space where we will be detecting these black holes. And together with more powerful simulations, we have really the prospects to unraveling their nature much more in details in the years to come. Thank you.
Thank you, Deborah. Questions for Deborah?
But it's going to be back in a second.
Parto da laggiù.
Hi, Deborah. Giacomo Venturi here. So very nice talk. And I have a question for you about the radio JETSI mergers. So can you tell how often would you expect radio JETSI mergers? Because I can recall a number of dual AGN with outflows from the observational point of view, but I cannot recall about the presence of jets.
So I'm afraid I don't hear the question. If somebody can repeat it closer to the mic, that would be fantastic.
So it's Giacomo Venturi speaking, and he is asking what is the cadence of these jets, what is the rate of these jets? The mergers, sorry, not jets, emergers, jets emergers.
Emergers, what is the duty cycle?
How often do
Is that the question?
How often do you expect jets in mergers from your simulations?
How often do you expect jets?
How often you will power the jets in a merger?
In your simulations, yes.
Yeah, that's a very good question. I don't have an answer to this yet. So these are the very first simulations that we have at all attempted to do with full a galaxy merger. So these simulations take...
Sorry. No, non funziona. Non lo dovevo fare.
To this, there is...
Sorry, Deborah, we lost you for 30 seconds because we had a glitch on the power.
Okay, shall I repeat?
Yeah, sorry for that.
Yeah, okay, no problem. So I just wanted to say that this was a really good question, and I don't have the answer to this because these are the very first simulations that we ever done with the jets and mergers. And they are extremely, extremely expensive, so they take 2-3 months a single simulation to run. And we had to do a lot of code development to run them at all in the first place. So the only way how I can answer this question at the moment is just tell you how often the jet is powered during this one single merger. And the interesting result is that there is a kind of low level of activity which is ongoing during the merger due to the similar arguments that I mentioned about the backflows. So as long as the material is able to circularize on the black hole, you power some low-level jet activity that actually promotes kind of ballistic orbits, and some material starts to fall back. And if you have an efficient cooling in the outflow, which we have implemented here to have a low temperature cooling to 10 Kelvin, essentially what that does, it's kind of repowering the jet. So we have a low level of jet activity. We don't really have jet really switching off during the merger. And then obviously we have a burst of jet activity at the coalescence that reaches a few times 10 to the 45 ergs per second for these massive disk galaxies. But it's a very good question. What would be occurrence of jets in mergers? We'll have to understand this.
Thank you. There is another question from Annalisa Celotti.
Hi, just a curiosity. So far, in your considering the physics of the feedback in cluster of jets towards clusters, are you considering magnetic fields?
Yes. So this is a very good question. So this is something that we are. This is something that we are planning to do. So we, within the framework of our code, Arepo, we have magnetic fields implemented, and we want to couple them with these our implementations of Landwehr jets, which we haven't done yet personally in our group. There have been other people that have looked into this. For example, the works by Rainer Weinberger, and they have contrasted some simulations. They have a bit different implementations of jets, and then they don't rely on the Blunt-Wassernaik model, but just in terms of kind of jets, energetics, mixing, and the jet appearance, they did find some differences when you go from ideal hydro to ideal MHD, but they actually haven't found substantial differences. So there is some effect of magnetic field draping, there is some effect on the mixing, but essentially you have to be equally very cautious about the resolution that you have in the simulations, not to have numerical overmixing, which is plaguing many of the models at low resolution. So we are definitely planning to do that, and then we will have also much more accurate representation of the synchrotron maps and so on. But we don't actually expect in terms of energetics and transfer of energy, what I have described, this thermalization of energy and then the transfer to the intercluster medium, we don't expect based on the works of others major differences.
Thank you, Deborah. Thank you very much for your presentation. I think we have no more questions from the audience. Thank you again. Let's thank Deborah.
Thank you very much, and thank you for having me remote. I really appreciate it. And again, apologies. I couldn't be there with you today. Thanks.
Thank you. So we move on to the next speaker.
Can you hear me?
Federica Ricci.
Yes.
Okay. Share.
Yeah.
Share
Federica,
screen.
I will tell you when you have 3 minutes left.
Okay. You can see my screen, right?
Yes.
Okay, perfect. I will start now then.
Sure.
So, first of all, I would like to really thank the organizers for the opportunity of giving this talk remotely. And today I will present you some work that is still in preparation about the molecular outflows and gas content of tubes cured the AGN at the golden epoch of galaxy evolution. So, after Deborah's review, I think we are all convinced that AGN feedback is a required mechanism to reproduce realistic galaxies in cosmological simulations. However, the physics, how these wide-angle AGN-driven winds propagate from the very inner region close to the central supermassive black hole out to the outskirts of the galaxy up to several kiloparsecs is probably still something that we need to better understand. And in order to do so, we should follow up the wind from the very inner region and up to the outskirts in its various phases, from the very highly ionized gas in the ultra-fast outflows in the center up to the neutral and molecular phases in the sub-millimeter, and then in the ionized phase. So in order to put constraints on feedback models. So, okay. So one prediction of this ejective mode feedback is that it should be able to halt star formation by removing gas or heating gas in the host galaxy gas reservoir. And so one open question is whether do we see such indirect impact on the host galaxy. And the answer, as also Ivan said in his review the first day, it really depends on whether we are looking at the high redshift, where studies have focused mainly on quasars, so on high luminosity targets, on high luminosity AGNs, where many works have found that AGN hosts are gas poorer than inactive galaxies, while in the local universe, many other works that focused mainly on Seyfert objects didn't find such a difference between the host, the inactive galaxies and AGN in terms of molecular properties, molecular gas properties. So there might be a luminosity or a redshift effect going on. So, as also Blessing said yesterday in her talk, we, in order to maybe understand better this problem, we need the right objects to target the right objects in the blowout phase, which is, as we know, short and X-ray active. And also, since the AGN wind is starting to pull out the material, there is still some obscuration, and therefore we really need to to select high luminosity and obscured sources. And for this reason, large area X-ray surveys with high quality multi-wavelength data is the key point to start from. And for this reason, we got ALMA data in the CO221 and CO524 of two obscured quasars with high luminosity exceeding 10 to the 46 erg per second, selected from the XMM cosmos. And these are the two quasars at redshift about 1.5 that showed already ionized outflows in the oxygen tree line, as you can see here. And these two galaxies, these two AGN that are XID 5395 and XID 5321 are actually hosted both in very massive systems, very massive galaxies of more than 10 to the 11 solar masses, but they are hosted in very different galaxies, one being a starburst with offset from the main sequence of 5, and the other one being a normal main sequence galaxy. So we got CO221 in order to test the indirect impact on AGN feedback, and then with the CO524, we hoped to get the molecular content part of the ionized outflow. So we start from the characterization of the molecular gas content from the CO221 data, and here you can see the offset of the gas fraction with respect to what expected from a main sequence galaxy as a function of redshift. For our two targets here, the yellow and red stars, together with a collection of high redshift AGN samples that are the other stars, and inactive galaxies samples, which are the green objects. So as you can see here, both XIDs have very low gas fraction, but also their offset is very large, more than 5 times below, or even higher, 10 times below the expectations, and this is indeed an indirect proof of the depletion of gas possibly due to AGN feedback. And if you want to see more about that, also in the CASHZ sample, I invite you to follow Elena's talk later on today. And also we can further see this indirect impact of the AGN feedback in this plane, showing the depletion timescale, again the offset of the depletion timescale with respect to what expected from models as a function of the offset from the main sequence for the same sample. And again, the location of 5321 cannot be explained without invoking AGN feedback, while for 5395 its location is possibly due to both the combination of AGN feedback and for its starburst nature. And for the overall AGN population, again, we see that they both have low gas fraction and low depletion timescales, lower than than inactive galaxies with matched stellar property, matched host properties, and the most deviating ones here. The most deviating AGNs here are the ones that show at least outflows in at least one phase. So now we also, thanks to the CO524 line, we detected indeed the molecular counterpart of the ionized wind, both blue shifted and red shifted for XID 5395, while only red shifted for 5321. and their location is mostly above the rotating disk, and co-spatial width was observed in the ionized phase, and these molecular outflows have indeed depletion timescales that are a bit between, let's say, 10 times lower than the depletion timescales derived considering only star-forming processes, and therefore this is a hint that these outflows can indeed quench rapidly the star formation. And we should also stress that there are very few such sources known at high redshift, and even lower number of objects showing, okay, thanks, showing both ionized and more than one phase of the outflow, let's say. So now in the last few minutes, I will show you the mass outflow rate, the molecular mass outflow rate as a function of some properties for a collection of AGN samples up to redshift 4. Here you can see these are color-coded according to the redshift. And so we start from the molecular mass outflow rate as a function of the star formation rate, and the diagonal lines are constant mass loading factors, 1 and 10 and 0.1. So you can see that both XIDs lie above the mass loading factor of 1. So this is telling us that the molecular outflows have enough energy to halt the star formation in their hosts. And then here we are you can see the mass outflow rate as a function of the bolometric luminosity. And again, I think that now we do see that there is a flattening at the high bolometric luminosity of the dependency of the mass outflow rate, as it was also first suggested in Manuela and collaborators' work back in 2019. And finally, here you can see the ionized to molecular mass outflow rate ratio as a function of the bolometric luminosity for the few sources that have both outflows. And you can see that for both XIDs, the molecular phase of the outflow is by far the one that is dominating the mass outflow rate, since this ratio is of 0.1 and 0.01. So I think that I am running out of time, and therefore I conclude here. But I just want to say that thanks to the both CO21 and CO524, we detected both the indirect effect and the direct, the molecular counterpart of the outflow, of the ionized outflow. And I think I will stop here and take questions, if any. Thank you.
Thanks, Federica.
Now I cannot hear you.
Wait, can you hear us? Can you hear us? Can you hear us? Can you hear us? Can you hear us?
Here.
Done.
Okay. Okay.
Okay, people were scared by the remote interactions, probably. Thank you, Federica. Thanks a lot. Ciao.
Thank you.
We now. Che è successo? Okay.
Thank you.
Okay, we now move on to the next speaker, Stefano Carniani, discovery of both self-gravitating and dissolved molecular clouds in a galactic wind.
Do you hear me? It's fine? It's okay? Yep. It seems someone say yes. Okay. So hello everyone. So we have this first talk in person of this morning. So we keep talking about outflows, but we move to the local universe. Higher? You don't hear? This is better? Perfect. Okay. Is on? Okay. After the first two talks, I think the engineering community knows that outflows are very important. From theoretical point of view, outflows can have a crucial role on the galaxy evolution, not just on the quenching framework, but could also are important to regulate the black hole growth, are important to enrich the GM or the intergalactic medium, and also, as Deborah showed, could also modify the morphology and the kinematics of the host galaxy. So, but this positive or negative feedback on the host galaxy is not the only things that outflows done, but there are also another impact, not on the host galaxy, but on its environment, in particular on the companion galaxy. This is a recent work done with my collaborator, Tommaso Zana, in which we analyzed two simulations, the same set of simulation, one with agent-driven outflow, one without agent-driven outflow, and we analyzed the evolution of the star formation rate of a companion galaxies, okay, that you can see there, and we noticed that when the outflow starts, the star formation rate enhanced, okay, and we don't see the same trend on the set in the simulation without the agent-driven outflow. This tells us that outflows are not only important for the host galaxy, but could also play an important role also for the environment and for the companion galaxy, and explain the bright galaxy that we see, the companion bright galaxy that we see in the high redshift universe. So from this slide, I'll explain you very quickly that we need to study outflows. And in the recent years, we know that outflow exists, and we need to carry out multi-wavelength observation, because gas in outflow could be very hot, up to 10 to 6, but could be also very cold. So several observations show that there is cold gas, molecular gas in outflows, and at least in the local universe and a low luminosity AGN, this phase of gas can contribute up to 90% of the total mass loss rate in the outflow, or 90% on the energetics of these outflows. The situation seems a bit different when we move to very in luminous AGN. Here you can see the trend, mass outflow rate versus volumetric luminosity for the ionized outflow and for the molecular ones. You can see that in very luminous AGN, the contribution of the molecular phase decreases, but still is quite high, and we need to study them. And there are several questions about outflow, about the cold gas in outflows. So if there is any relation between the warm and the cold phase, what is the origin of this outflow? Several simulations try to reproduce the observation, but most of them fails because the clouds are not able to survive on the outflow environment. And then we will know the fate of this cold fast gas. So most of the observation targeting molecular outflows just focused on very bright AGN on the high redshift universe. And so what we see only is the presence of the wings, and maybe from the image we see a blobs. We are not able to spatially resolve the emission. Therefore, we decide to study the local galaxy. In particular, today I'm going to show you the observation carried out with Muse and ALMA, Muse to target the ionized phase and ALMA to target the cold phase of a local galaxy called NGC 4945. that is a starburst galaxy with an AGN at the center. Okay, despite the angular resolution is not quite high, it's 0.6 arcsecond, thanks to its distance, we can study the outflows with a resolution of parsecs. Okay, we start from the ionized phase. This is the map of the outflows from the broad wings of the nitrogen 2. You can see the two cones, the blue ones, so in which the gas is approaching along the side, and the red cones in which the gas is going far away from the along the line of sight. In this case, from the red cone, we didn't see only part of that because the emission is obscured by the dust in the galactic disk. Okay, this is what we expect, and this is perpendicular to the galactic disk, and this extension is about 0.4 kiloparsec. So this is what we expect, biconical outflows. So thanks to this observation, we can also study the kinematics pixel by pixel. Okay, this is the velocity map of the ionized outflows. And what we have done, we try to simulate by using a toy model, a biconical outflows, in which we can change the inclination, the opening angle, the size, the velocity dispersion, the outflow history, the velocity, and so on. Okay, and we use this simple model to reproduce our data. Okay, and what we found is that the data we can very well reproduce by using a biconical outflows, with an alpha open angle of 38 degrees, a size of 0.23 kiloparsec, a velocity that is almost constant over the size of the outflows, and inclination about 78 degrees. So this is quite normal. So this is what we expect from an outflow, a biconical outflow. So far so good. So now we want to look at the molecular phase. So from the ALMA, we observe the CO2-1 lines. We see the emission of the narrow components with velocity below 250 km per second that they trace the rotating disk. The velocity map is here, and here we can see the channel maps of the narrow component. And then we see the presence of the broad wings with velocity higher than 250 km per second that trace fast gas, also this one perpendicular to the disk, the galactic disk. So, and if we overplot the molecular outflow over the map of the ionized ones, we see that the two phases are aligned, okay? But the molecular phase is less extended than the ionized one, okay? While the ionized one is up to 0.4 kiloparsec, the molecular outflow is extended up to 200 parsec, even less. There are several clamps more extended. Okay, we discuss it later. Also, for this observation, we can study the kinematics, and we can compare with the one of the ionized gas. Okay, this is the ones that I showed you on the previous slide. And this is the velocity map of the molecular outflows. So the two maps are completely different. Okay, in this case, we can see more or less blue. The color bar is the same. Here in this case, we see more or less a gradient of velocity from red to blue. And indeed, if we use the same model to reproduce these kinematics, we are not able to find the right parameters to reproduce this observation. The only way to reproduce this map is to use two components. One, a radial component, so the same model that we use for the ionized outflows, plus a circular component similar to the ones of the galactic disk. In this case, the morphology of the velocities are similar to the one of the data. This tells us that the molecular outflow is rotating. It's a rotating molecular outflows, and it shares the rotation velocity of the galaxy. So this means that the molecular clouds in the outflows are not formed in situ in the outflow itself, but they are the ones that are in the galactic disk that are accelerated by the warm gas up to high velocities. This is about the kinematics. Now we see the morphology. So thanks to the high resolution, we can see that the molecular outflows is formed by several clumps, okay, with very small size, okay, below 10 parsec. And if we extract the spectrum of one of these the spectrum of the CO2 spectrum from one of these clouds, you can see an example here, we can see that the spectrum is very narrow, and this tells us that the wings that usually we see in the outflows are just the sum up of these individual clouds for which the velocity dispersion is quite small. We can compare these properties also with the classical properties of the giant molecular clouds that we see in the Milky Way or in local spiral. And this is what we see in this plot. Here we have, from the left to the right, velocity dispersion versus CO luminosity, size versus CO luminosity, and virial parameter versus gas mass. The virial parameter is the ratio between the kinetic energy and the gravitational energy. This tells us if the clouds are self-gravitating or not. In particular, if the parameter is below 2, this means that the clouds is self-gravitating. Okay, as you can see, and the blue points and the red points are the properties of the giant molecular clouds in the Milky Way and in nearby spirals. These are our points, our flowing clouds. You can see that they are very turbulent. It's fine, okay? These are clouds in the outflows, so we expect they're turbulent. But at the same time, are very compact, more compact than the classical GMC. And some of these clouds are also self-gravitating, can survive for a long time. They don't dissolve. This is consistent with a scenario in which these clouds are accelerated by the warm gas, and the radiation of the AGN start to turn the shell of the cloud in atomic form, okay? So destroy the clouds. We have a photoevaporation. So the cloud lose mass, but at the same time, these induce an implosion and a gravitational collapse. So the clouds start to be very small, compact, and dense. Okay, and this is what we see. We use this model to produce our data. Okay, these are the properties: mass, distance, radius, distance, and density versus distance. And these lines are the models and show that the evolution of these molecular clouds accelerated by the warm ionized gas. So in principle, for different initial conditions. Okay. So what happens is that after a few less than 1 megayear, these clouds dissolve, most of the gas in these clouds is dissolved, but there is a part of this gas that is very dense and can cool form stars. In this case, we have this outflow in these clouds. Stars can form a very high velocity, and if its velocity is higher than the escape velocity of galactic disk, this can escape from the galactic disk, otherwise can start oscillating around the galaxy and form the spheroidal component. So this is a new mode of forming stars. And with this, I leave you with my conclusion. So these nice observations show that molecular outflows are formed from self-gravitating clumps in which stars could form. Thank you.
Okay, times for questions.
Ciao Stefano, can you hear me?
Yes.
Beautiful data. Regarding the molecular gas kinematics, I was wondering whether you can explain it with a steeply rising rotation curve towards the center, whether you really need an outflow rotating component that seems a bit strange.
I mean, you want to explain with a different circular velocity, no, or with a different profit?
Yes, I mean,
Yes,
It's clear that the molecular gas, the high velocity component of the molecular gas, has the same orientation as the disk and is perpendicular in kinematics. At least that's what I see.
Yeah.
It's perpendicular in terms of kinematics with respect to the ionized cone.
Yep.
So I wonder whether that is just residual rotation in the center.
From the gravitational potential of the galactic disk, we cannot able to reproduce the velocity maps, because the peak of the velocity of the circular velocity of the galactic disk is up to 200 kilometers per second. So in principle, we are not able to reach this high velocity without adding this radial component to the model.
How do you know a priori what is the circular velocity in the center? I mean, that is plus or minus 300
this
kilometers per
is
second.
study from sorry. Yes, this is study from other work, study the narrow components, the central part, from different tracers, in which they clearly determine the circular velocity of the narrow part with higher angular resolution. So this is just already done from several other work. So we use the same result, in which they provide the circular velocity, projected ones, up to very small scales, and we use this circular velocity to reproduce our data. Okay, maybe we discuss it offline.
Thank you. I actually had the same question, and I'm not still convinced about the answer, but the other question I had is, it's not very clear to me what you mean by the ionized gas that accelerate the molecular gas. How does the ionized gas accelerate the molecular one?
So just the pressure, the momentum that the warm gas, mechanical, yes.
Other questions?
I was curious in the geometry when you show the angle of 60 degrees. Is that attributed to, is that orientation generated when the outflow is launched, or is related to the structure of the galaxy itself?
So this inclination here, you mean?
Yeah, because the cone, you in your model you reproduce the orientation of the cone. So I was wondering if it was generated with this orientation, has to do the structure of the galaxy and the other material around. If you can tell that.
No, this is generated only based on the outflow data. So we don't care anything about the galactic disk properties. So this is just the data that we see are just the emission of the outflows. And by using this simple toy model that could be more complex, we determine the inclination of... It's consistent with the galaxy. Yes, it's consistent with the galaxy. It's more or less, yes, it's perpendicular to the galaxy disk. Okay, but we didn't fit together, so are independently measurements.
Yeah, the ionized cone is perpendicular to the galactic disk. So the molecular gas, which is within the ionized cone, is very likely above the galactic disk. It's not part of the galactic disk. And this is one of the ionizing cones which originally was not thought to be related to the NAGN, but just the cone created by an outflow driven by a starburst at the orbital side. So it's really perpendicular to the galactic disk in the direction of the minimal resistance. Yeah, the molecular phase is not part, the ionized, the high velocity one is not part of the disk. It's above of the disk. Okay. Okay. We now move on to Manuela Bischetti, suppression of black hole growth by strong outflow at redshift 5.8, 6.6.
Okay, thanks. Can you hear me? Okay, great. Good morning, everyone. After this beautiful data from the local universe, let's now move to very high redshift. I will talk about the discovery of a large number of outflows in redshift 6 quasars. After this morning introduction, I don't need to recall you that feedback from black holes is typically invoked from models of galaxy formations to explain the low efficiency of star formation rate in the context of massive galaxies. What I wanted to recall is that the fact that we observe massive quiescent systems, already a redshift of 3 up to 5, indicates that some sort of feedback mechanism must have been in place even at earlier epochs, so at redshift as high as 6, for example. And as we aim to discover these outflows at high redshift, one useful approach is to target hyperluminous quasars, because as you can see from this compilation of black hole-driven outflows, here you have the mass outflow rate, which is essentially the outflow strength as a function of the AGN luminosity. It is in the brightest sources that you expect to observe the most powerful outflows, which are thought to be responsible for suppressing the star formation activity by heating, displacing, removing gas for the black hole surrounding, or even from the host galaxy. So I also wanted to recall the well-known relation between the mass of supermassive black holes and the mass of host galaxies that we observe in the low redshift universe. That is this black solid relation that you can see here. However, if you put redshift 6 quasars in this plot, you can see that they are about a factor of 10 over massive with respect to their host galaxies. So essentially this is telling us that they must have grown more rapidly than their host galaxies during the first giga-year of the universe. So theoretical models of early black hole and galaxy formations in massive halos expect that the almost exponential growth of black holes at very high redshift may start changing at redshift of about 6, and in particular may start slowing down. But although suggested, these have never been either confirmed or ruled out by observation so far. A useful method to probe ionized outflows up to very high redshift can be looking at broad absorption line features in the rest frame UV spectrum of quasars. You can see here one example for a quasar at redshift about 6. So these BAL features are broad, so broader than 2,000 kilometers per second absorption, associated with high ionization lines such as carbon 4, you can see here, silicon 4, nitrogen 5, that typically have velocities of 1,000 kilometers per second, tens of thousands of kilometers per second, and these absorption features trace outflows, which are expected to arise close to the accretion disk However, observations of BAL quasars at high luminosities have shown that the absorption can occur at much larger scales, up to hundreds of parsec. This tells us that BAL outflows may be an important source of feedback on both the growth of the black hole and on the growth of the host galaxy. So what we did was to go for the first systematic investigation of BAL outflows, a redshift of about 6. And to do so, we exploited unprecedented quality observations from the XIV legacy survey of quasars at reionization, XQR30, which is based on an ESO large program with XIV of almost 250 hours, aimed to target a statistical sample of 30 quasars at redshift between 5.8 to 6.6, luminous quasars with high signal-to-noise observations. So I will show you the main results from this work that has recently appeared in Nature. The first result is that we find widespread presence of outflows in the redshift 6 quasars. As you can see here, we observe BAL features in about half of the sample, and we also build a control sample of lower redshift quasars with similar selection criteria, similar luminosity, and this has allowed us to assess that redshift 6, the BAL fraction, is significantly higher by a factor of about 2.5 with respect to what observed in redshift 2 to 4 quasars. And this difference remains valid even if you select control samples to match the nuclear properties such as black hole mass and accretion rate. So this is telling us that there must be a redshift evolution of the BAL properties, either in terms of geometry, so essentially wider angle BAL outflows at high redshift, or in terms of time scale, so longer quasar blowout phases at high redshift. But this is not the only difference that we found. We also found that these outflows in redshift 6 quasars are significantly faster, the one observed the lower redshift, and they typically have extreme velocities in the range 20,000 up to 50,000 kilometers per second. So we may argue that BAL outflows at redshift 6 are more easily accelerated with respect to lower redshift. And one possibility is that there is dust mixed with the BAL clouds. And this might be a viable hypothesis because we observe a systematic difference in the race frame optical colors of BAL quasars with respect to non-BAL quasars at high redshift, while we essentially see no difference between these two populations in the lower redshift control samples. So this suggests that there might be a difference in terms of dust properties. In any case, because of the higher BAL fraction and because of the higher velocities, BAL quasars at high redshift globally inject about 20 times more energy than what is observed in lower redshift sources. So this points towards a strong black hole feedback, likely suppressing black hole growth at early epochs. So as I was telling you at the beginning, we expect that the black hole growth dominates the growth of the host galaxy at very high redshift. So you essentially have quasars moving almost vertically in this black hole mass versus galaxy mass plane, but we do observe strong black hole feedback at redshift 6, likely suppressing the growth of the black hole. So an intriguing idea is that we might be observing the key epoch of the onset of the symbiotic growth between black holes and galaxies. The missing ingredient to either assess or rule out these hypotheses is the star formation rate from the galaxy, because current observations suffer from systematics that do not really allow us to discriminate between these two scenarios. And for example, high-frequency ALMA observations probing the peak of the far-infrared dust emission would really help us to know more. And we have proposed observations for these. And these will tell us whether BAL quasars can be used as tracers of ongoing feedback at early epochs. So stay tuned. I stop here and leave you with my conclusions. Thank you.
Thank you very much, Federica. We have time for questions.
Ciao Manuela. You said that
I'm already accused at the beginning of the morning. This is not good.
But it's the last day. So.
The last day, okay. Thank you.
So you said that the larger fraction could be due to a geometrical effect in the sense that the bulk could be wider opening angle. Can it be instead that you are seeing these objects with a preferential orientation?
It could be, but we also checked for the width of the BAL absorption, and you see a redshift evolution. So this may be pointing towards a geometry evolution with redshift. They become broader. You have the divergence angle of the BAL in the standard model by Elvis, and you would expect about 20 degrees for the angle at redshift 6.
Very nice talk. I guess you have to model the continuum and the emission lines shapes. Do you see some differences in the continuum slope and in the blue shift of the emission lines with respect to low redshift or non-bulk quasars?
So what I did, was to build a composite template, as you say, as the product of hundreds of non-BAL SDSS spectra. But what I did was to individually match each composite template to the spectrum I wanted to analyze in terms of equivalent width of the carbon 4 line, because this also accounts for the redshift, the blue shift of carbon 4. So it is nice to properly model this region of the spectrum. And I also matched the template in terms of slope. So I required the template to match the spectrum around here and in the bluest region in which I can probe some continuum, because of course at high redshift I do not have, I have no continuum blueward of the Lyman alpha. I do not know whether there is a systematic difference in terms of, for example, carbon-4 equivalent width between high redshift, low redshift sample. But what I can tell you is that the redshift 6 quasars also show large blue shifts of the carbon-4 thousands of kilometers per second, as we see in the luminous quasars at lower redshift.
So we are running out of time, so there are two very good questions, right?
Actually, no, that's fine, because mine is a comment.
Hi, Manuela. A very nice talk. I was wondering, if I understood correctly, these black holes are quenching themselves, and then the galaxy will slowly transition to the black hole scaling relation, essentially only growing in mass, in stellar mass, without a further growth of the black hole, right?
Well,
okay. The question was, if this is correct, how does the galaxy grow without further feeding the black hole?
Okay. No, so essentially, the idea is that I observe the quasars up here. So I know black holes must have grown more rapidly in the initial phases, okay? And then if you take a sample of luminous quasars at redshift 6, you see, as you know, the luminosity, the black hole mass of these sources, you can estimate the ratio between the black hole accretion rate and the black hole mass, which gives you an idea of the black hole growth, and you compared with the star formation rate of the host normalized by its mass. And there are sub-millimeter data that tells you that the galaxies are growing at hundreds of solar masses per year, and also the black holes are accreting at Eddington. Okay, very close to Eddington, so they still accrete. But the key point is the balance between the two, because and we are in a regime in which if you have a star formation rate of about 100 solar masses per year, the growth is still dominated by the black hole, while if you have 1,000 solar masses per year, these objects may be starting to approach the local relation.
Okay, thank you, Manuela, not Federica. We now move on to Giulia Tozzi, linking galaxy scale widths with nuclear ultrafast outflows from low to high redshift. I will tell you in 3 minutes.
Thank you very much. Okay. So good morning, everybody. My name is Giulia Tozzi. I'm a PhD student at University of Florence, and this is my first AGN conference, so I'm very happy to be here. And so today I'm going to talk to you about the connection between galaxy scale winds and nuclear ultrafast outflows in low and high redshift quasars. And these are the people. These are the people who contributed the most to the work I'm going to present. They have been all attending the conference, and they are quite popular in the AGN community. Okay, sorry. Okay, so let's start from a bit of introduction. In the framework of the so-called wind feedback models, a fast nuclear wind is predicted to accelerate, to shock against the interstellar medium, and so to accelerate an outflow on larger scales. And from an observational point of view, these inner winds are identified in UFOs, which are ultrafast outflows typically detected in the X-ray through strongly blue-shifted absorption of highly ionized metals, typically iron. And then, depending on the cooling efficiency in the shock gas shell, we distinguish between two main propagation modes. A an energy-driven wind in the case the cooling is negligible. And in this case, the feedback is very effective at sweeping up a significant amount of gas in those galaxies. While if the gas, the shot gas, cools efficiently, we have a low efficiency feedback because the accelerated ISM receives only the momentum of the inner wind. And so in this case, we talk about a momentum-driven outflow. Okay, so these are the two works I'm going to show you, Marasco et al. 2020 and Tozzi et al. 2021. Two works we conducted almost in parallel with the common aim of investigating the link between UFOs and in particular the ionized phase of large-scale outflows. In Marasco et al. 2020, we did it locally into local AGN, where a higher spatial resolution can be achieved, as well as a more detailed description of the outflow and its properties. While in Tozzi et al. 2021, we did the same, but in two quasars close to the peak of both AGN and star formation activity. So that is a crucial epoch for the study of feedback. And oops. Okay, so a starting point, we selected the object with a clear UFO detection in their X-ray spectra, obtained with several X-ray facilities. And so for the two local AGN are two bright type 1 Sievert at redshift 0.26, while the two high redshift ones are at redshift 1.5, and they are lensed systems. It was just thanks to the gravitational lensing that it was possible to obtain X-ray, high-quality X-ray spectra with a clear signature of UFOs. And then to map and study the properties of the ionized gas on larger scale, we use integral field spectroscopy. And in particular, we use Muse adaptive optic observations in narrow field mode for the two local AGN, and near-infrared symphony observations for the two high-redshift quasars, unfortunately in sync limited mode. And okay, so for the analysis of both Muse and Symphony data cubes, we use our custom-made fitting procedure that is well described in Marasco et al. 2020. It consists of two main steps. A first modeling of the full spectra in order to identify and to remove the overall unresolved AGN emission. So basically, the AGN continuum plus the borderline region emission. And then, after this removal, we perform a finer modeling of the narrower emission lines from the diffuse ionized gas using multiple Gaussian components and taking care also of properly classifying each Gaussian component as either a narrow systemic component or an outflow component to be then confirmed by the kinematical analysis. And these are the moment maps for the two local AGNs, and relative for both the oxygen 3 and the H alpha. And in each set of plots, you have the first column referring to the total line emission, the second one to the narrow component, and the third one for the outflow. And now, focusing only on the kinematics, you can see that the narrow component shows a clean and regular velocity field and low sigma values. And in particular, the narrow component traces in PG 1126 traces regularly rotating gas, while in MR 2251 it is possibly associated to tidal debris from a recent merger or flyby. While about the outflow component, you can see that it's concentrated towards the center, and it's extended up to a few kiloparsec from the center, with high velocity dispersion values and blue shifted velocities ranging from a few tens to a few hundred kilometers per second. Now, coming to the two high-redshift quasar, well, I have to remind you that they are lens objects, and so these maps are in the plane of the lens, so they are not representative of the intrinsic morphology of both the outflow and the diffuse ionized gas. And moreover, these are not only lens objects, but they were very problematic from a gravitational lensing point of view, because the problem with HS0810 is that if you compare the Symphony maps with the HST map, we didn't spatially resolve the images, while in the case of J1353, actually here you can see only one image, because we didn't detect oxygen 3 from the southern image. So these are maps relative to the northern image of the quasars. And from a kinematical point of view, okay. The outflow component shows in both cases higher velocity values and also velocity dispersion values. Okay, so then we computed the mass outflow rate using this formula, and okay. The out is the outflow velocity, for which we took percentile velocities corresponding the extreme tail of the lines, and then we have the mass outflow, the mass of the outflow derived from the oxygen 3 flux, which depends on the electron density, which we computed from the sulfur 2 doublet for the two local AGN, while we assumed to be equal to 1,000 per cubic centimeter. And then we have also the outflow radius, and both the outflow radius and the oxygen 3 flux were corrected for lens effects in the case of high-redshift quasars. And then, okay, so with all these ingredients, we calculate all the other quantities reported in this table, and then comparing with the energetics of the UFOs, we found that in 3 out of 4 objects, the energetics is consistent with the momentum-driven regime. And in the case of, in the case of HS0810, we also considered the contribution of the molecular outflow detected by Allman, and in this case, the measurements becomes consistent with an energy-driven regime within the large UFO uncertainty. And so the last, instead, the only... I'm terrible. Instead, J1353 is the only object whose energetics differs of about 2 orders of magnitude from the theoretical predictions. This requiring either a massive molecular outflow or a high variability in the AGN activity of this galaxy. And then to put our results in a broader context, we consider our results along with those obtained for a small sample a small sample of AGN from the literature with clear detection of both UFO and large-scale outflows. And this plot shows the ratio between the outflow momentum rate over the momentum rate of the UFO. So a value of 1 corresponds to the prediction of momentum-driven wind, while the orange rectangles are the prediction for each object for an energy-driven an energy-driven wind. And what we found is that 10 out of 12 quasars are compatible with one of the two mechanisms, so suggesting that these two models, in spite of their simplicity, are able to explain well the mechanism which propagates outflows. And then after a week of talks, now there are new objects under study, so this plot should be updated, and yes, and this is my last slide with my conclusions and take-home messages. And in particular, I would like to stress the fact that we need to keep on enlarging the sample of AGN hosting both UFO and large-scale outflows. And this must be done both at low redshift, where a more detailed description of the outflow can be achieved, but also at high redshift, with particular focus on redshift 2, so the key epoch for feedback. And finally, I would like also to mention the importance of carrying out multi-wavelength observations because they are essential for to obtain a complete multi-phase description of AGN winds, so in order to do a proper comparison between observations and models. And we have recently submitted an annual proposal to study the molecular phase of the outflow in the three objects, both the two local AGN we studied and in J1353, in order to trace this missing gas phase. And I stop here. Thank you.
Thank you, Federica. Sorry, I have to get wrong also your name just to be even. Questions?
No, it's just that it's not a question specific to your talk, but a general comment that I wanted to make before also. Sorry. It's just a general comment, which I want... does it work? No? Okay. I'm starting to... I mean, if you want, I do have a question to everybody who works in this field. Do we have any real clear evidence that molecular outflow are somehow related to BAL, UFO, to objects that move at completely different velocities? Because from what I see, I mean, there are, you can put momentum-driven, energy-driven, whatever you like, and it seems like sometimes it works in a way, sometimes it doesn't, sometimes... So all these, to me, seems more like the two phenomena are completely unrelated, perhaps.
Do you mean the acceleration of an ionized outflow and a molecular outflow?
When you really look, when you can resolve things, you always see velocity of 100, 200, 300 kilometers per second, and then suddenly you see also in absorption without resolving the scale, you see a velocity of 10,000, 20,000, 0.3 C, completely different phenomena they would look like to me. And so I think perhaps we are really looking at some very innermost phenomenon at very subparsec scale in the AGN, and then something else triggered by star formation, stellar winds, or whatever. But I mean...
Okay, I get your point.
I mean, just to reply partially, I think it's early to answer your question, so it's not clear if there is a clear connection. So this kind of works, I mean, there is just 12 objects where we have, at the same time UFOs detected and large-scale outflows, but then just the fact that somehow their centrities here are very large. So all your computation of your mass outflow rates and energetics is very uncertain. But the fact that more or less
yes,
the scaling is similar, but a few
yes, I mean, in these objects,
somehow this could be related. But this, I think, is too early to say anything firm. But that's why it's useful to go on observing this object and
maybe
have,
we
instead of 10 having 100 objects, and then we can discuss if these are clearly related or not. But I mean, the first indication is that, I mean, this plot tells me that somehow this can be some kind somehow related to phenomena. But I mean, I think that it's still early to saying anything more firm.
And then there is the issue of the time scales. What the UFOs we are seeing now could be different from the UFOs that were directly related to the one over there. Okay, so there are no more questions. So first, before going to the coffee break, do not forget when you leave to leave the badge to the desk. It's a magnetic badge, so you have to return it. What is inside your badge? Magnetic card. And then we reconvene at 11:15. Let's thank the speakers of the morning. Hanno già ringraziato.